Hello everyone, warm welcome. Thank you for joining. Get yourself ready with a notebook, a pencil or pen. Anything you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today, for you BC students that are struggling with power series representations and building functions, we're going to take a look at how to do that. But first, we're going to give you a chance to review the main power series representations that you will need. So let's go over these together. We have the series for 1 over 1 minus x. That's a specific structure of an equation. And this is represented by the easiest series, the geometric series, with a radius of r. So whatever this x is, that's kind of like the multiplier. See how each term is being multiplied by x to get to the next term, and they're all being added. Okay, pretty basic. Now, e to the x, interestingly enough, is very similar to 1 over 1 minus x. You'll see the similarity, but each term needs to be divided by n factorial. So the representation is very close. You see they're almost the same. The sum of all x to the n, but then over n factorial, so that each term carries this. And again, this is a structure. It doesn't have to just be x. It can be 7x in there. It could be a different amount of x, which they make a note of here. You would just plug that in accordingly. Cosine, which we know is an even function, has this representation of all of these even powers, but they alternate. So it's kind of like e to the x, but we're only taking the even terms, and they're alternating. So we're going to take this x to the n, and we're going to change it to an x to the 2n, because these are increasing in power by 2, right, as n goes up. And of course, on the bottom now we have 2n factorial, because all of those terms are doubles. And as n goes up, 1, 2, 3, we have 2, 4, 6, right? And then here's the alternating component. So sine has a very similar representation, but sine is represented by this with x to the 2n plus 1 over 2n plus 1. So we still see some alternating. Basically just multiply these terms by x and increase the n basically by 1. That's all you do. You increase the n by 1. So it's the same kind of series really, except it's taking x to the 2n plus 1, sorry to cover that, and then 2n plus 1 factorial on the bottom. So they're very similar. We have ln of 1 plus x. So 1 plus x needs to be a 1 plus, just like here it needs to be a 1 minus. If you need to manipulate your expression, you may have to do that. Ln of 1 plus x, that's going to turn into this, which is alternating. It's almost like e to the x, but notice that this is n factorial on the bottom, and it doesn't alternate, whereas this does alternate. And not only does it alternate, positive, negative, but these are not factorials. These are just n. So it's not n factorial on bottom, it's just n on bottom, which we see here. We see this alternating -1 to the n plus 1. The powers on x are just increasing as n increases, and we're dividing by a number, not the factorial of that number. Tan inverse, not really used that often, but it's possible that it can come up. So it's very similar to ln of 1 plus x actually, but the difference is, just as the difference between cosine and sine is that we have 2n plus 1 instead, we're going to be doing that. We're going to have 2n plus 1 instead here. See how these are very similar, except the denominators and the powers are different. So this is n and n. This is 2n plus 1 and 2n plus 1. n and n, 2n plus 1, 2n plus 1. Okay. Oh, and really important to point out that if you're going to shift it like that with sine and also with this tan inverse, that you need to take it from n equals 0. If you wanted to use 2n minus 1, you would go from 1 to infinity. But if you want to use 2n plus 1, you have to go shift the n's. Okay, that's a little recap on how we're going to use those, or on what we're going to use really. Now let's practice on how to represent these. So the goal is just to write a few terms of this out. So we're going to call this one 1 over 1 minus. So 6x is acting like my x. Remember, this is going to be the geometric series with an r value of whatever this thing is. So we're going to have plus 6x plus 6x squared plus 6x cubed, so on and so forth. We can call this the sum n equals 1, 2, or did they go to 0 on here? I think they went to, yeah, they started at 0 with this one. So let's go from n equals 0. You could do it from 1. It's not that different, but n equals 0 to infinity. You would just call this 6x to the n minus 1 if I started at 1. But since we're starting at 0, we'll have it go 6x to the n. And if you wanted to write it, you can write it as 6 to the n, x to the n. And then you can go ahead and find like an interval and radius of convergence and all that good stuff, but that's not what this video is about. So you're not going to do that. Okay, let's look at a slightly tougher one here. Let's look at something like, I'm looking at this one, number 9. Looking juicy. All right, we need to use the fact that e to the x, right? Let's take the 1 over x out for now. Let's take the fact that e to the x is going to expand how? We increase the powers, but remember, we need to divide by the factorial of n. So this is going to be 1 plus x squared over 2 plus x cubed over 3 plus ... Then we're going to subtract cosine, which means we're going to subtract this alternating x squared, but remember that cosine is going to be over the factorial. So let's be over 2 factorial, right? Cosine is an an even function with these even powers, but we are going to have the factorials tracking on the bottom. So just keep that in mind. And then we're going to have plus x, 4 over 4 factorial minus x6 over 6 factorial plus ... So what are we going to get when we subtract these terms? Of course, the 1's cancel. That's no surprise. But you'll notice a pattern, as expected. We're going to have x plus x squared over 2. Maybe I should take the x squared out and call this 1 over 2 factorial plus 1 over 2, which those happen to be the same thing. And then what are we going to get for the next term? It's going to be plus x cubed over 3. Those are untouched. These odd powers are untouched by the cosine because cosine only has even powers involved. So then we're going to have, this would be x to the 4 over 4, by the way. Then we're going to have, let's factor that out. This is going to be 1 over 4 minus 1 over 4 factorial x to the 4, and then we kind of have a pattern here. So we see that this term is going to be a positive on the factorial, this one's going to be a negative on the factorial, and it just kind of alternates like that. So if I wanted to put some more terms, this would be x5 over 5, and then I would have positive 1 over 6 minus 1 over, plus 1 over 6 factorial, x to the 6th. Then we would have x to the 7 over 7, and then this next one would be 1 over 8 minus 1 over 8 factorial, x to the 8th, and so on and so forth, right? If we divide all of this by x, we're just going to end up with 1 plus 1 over 2 plus 1 over 2 factorial, which again is 1 over 2 as well. This is going to be x. All of these powers are going down. X squared over 2 plus 1/4 minus 1 over 4 factorial, but this is now times x cubed plus x to the 5th over 5. And that's enough terms. I think we kind of understand the pattern here. This would be an appropriate function. Now, if they told you to get a second degree or third degree, or this would be x4 over 5, or whatever degree polynomial they want you to use, you can pick whatever level of precision you need. So do you see how that worked? What I did was I took e to the x and I subtracted cosine to the x's terms, of course, only if they're common terms. So the squareds can go together, the fourths can go together, but the odd powers of e to the x do not get tampered with. And then we divide everything by x at the end. This is how we build functions. Okay, I think we'll do probably one more together, and then I'll let you try some of these for your own. I think, by the way, this is supposed to be cosine of 2x. I think. It's definitely not supposed to be COX, or cos of x2x. That would just be cosine of 2x squared, for example. So this has to be a cosine, right? Okay, maybe number 12. Number 12 is also looking a bit tricky. So this is going to be just x times the expansion, but it's the expansion on e to the negative x squared. It's not just e to the x. So we got to be careful, because it's not just going to be x plus x squared over 2 plus x cubed over 3. That would be nice, but it's going to be 1 plus negative x squared plus negative x squared quantity squared over 2 plus negative x squared cubed quantity, negative x squared quantity cubed over 3 plus negative x squared quantity to the 4th over 4. And I think that's probably enough. Let's work these out a little bit. So this is 1 minus x squared plus x4 over 2 minus x6 over 3 plus x8 over 4. And of course, these are all multiplied by x. So we can just increase the exponent on all of these. Very simple. It's still going to alternate. It's just that now it's going to alternate one level higher, you might say. 7 over 3 plus x9 over 4 minus x11. See, we're just adding 2 to the power, and we're just adding 1 to the bottom, and we're making sure to alternate. That's all there is to the game. So subtract, and then plus 2 on the power, and then plus 1 on the bottom, and then plus 2 on the power, and then plus 1 on the bottom, and then minus. You get the idea. Now, they'll probably ask not for a 17th degree polynomial. They'll probably ask for like a 5th degree, to use a 5th degree, and they're only going to have you plug in reasonable numbers like 1 or maybe 2. They really won't expect you to be doing like 2 to the 9th, 2 to the 7th. It's doable. It's not easy. You just multiply 2's, but I think that that's a realistic expectation, even from the AP exam, that they're not going to have you do like the 11th degree polynomial. Okay, so if you'd like to try any out, I do highly recommend some of these problems, something like 1 minus sine of x squared, for example. That could be a good one, and I really think this might be a little bit deceiving. It's a lot easier than it looks. So I leave you to try these exercises. Of course, practice is what makes you better. Watching me doesn't necessarily make you better. It may be helpful. I can do these problems till I'm blue in the face. That won't make you necessarily that much better than just practicing and trying it for yourself. So if you have any issues, do let me know. I'm open to feedback, and I'll see you next time in the void.